Hey, Honors Chem students, today's lesson involves stoichiometry, which we had a little bit more challenging assignment over the weekend. Hopefully, you did well on that. And now we go to the limiting reactant side of stoichiometry. And this will be a very good video to watch because it will show you a little bit of a different technique on how to use stoichiometry tables than what we've learned thus far. Once you get the technique down, I think limiting reactant problems will be easy and you'll have some practice to do after this PowerPoint. So let's act like we want to make some sandwiches for lunch today while you're at home, and that the ingredients to make a sandwich will be 2 slices of bread, typical, 3 slices of meat, and 1 slice of cheese. So I want to give you some examples of what you might find in the kitchen today to make those sandwiches. We want to look at the ingredients on the next slide and see the number of sandwiches we can make and what we have in excess, what is left over. So here's our first situation. I got 6 breads, 10 meats, and 4 cheese slices. If we just look at the bread, just at the bread alone, we can make 3 sandwiches. If we look at the meat alone, we can also make 3 sandwiches, but we'll have some meat left over. And if we just look at the cheese, we can make 4 sandwiches. So I can make 3, 3, 4 sandwiches if I look at those alone. So overall, I can make 3 sandwiches, and I have no bread left over. I have 1 piece of meat in excess, and I have 1 slice of cheese in excess. So we would say that the bread limits us in making more sandwiches. Next situation, I have 10 bread, 6 meats, and 8 cheeses. So if I just look at the bread alone, I can make 5 sandwiches. If I look at the meat, I can only make 2 sandwiches. And if I look at the cheese slices, I can make 8 sandwiches. So you can probably guess what's going to limit us on this situation, and that will be the meat. We can only make 2 sandwiches because we only have enough meat to make those 2 sandwiches. When I do that, I'll have 6 breads left over and I'll have 6 cheese slices left over. So the meat limits us, and I have excess bread and excess cheese. Last situation, we're having a party. We have a whole bunch of people over to the house. Obviously, not today, tomorrow. It's going to be a few months before we have a whole bunch of people to the house. But anyway, with those 25 breads, I can make 12 sandwiches. With those 40 meats, I can make 13 sandwiches. And with the cheese, I can make 12 sandwiches. So I can make 12 sandwiches overall. I'll have a piece of bread left over. I'll have 4 meats left over. And my cheese will limit the number of sandwiches I can make. My bread and my meat are in excess. These real life situations are exactly how we want to think about limiting reactants when we talk about stoichiometry. So, limiting reactant. Notice the word reactant first. That will be anything to the left side of the arrow in a chemical equation. Limiting reactants are totally used up when we do the reaction in real life. There's nothing left over. And whatever limits us will determine the amount of product that we can make, just like the sandwich situation. One of those ingredients always limited how many sandwiches, how much product we could get. On the other side of limiting reactants, there always will be an excess reactant. Excess meaning too much. So that will be the reactant that we don't completely use up. So in every one of those sandwich situations, we either had some bread left over, we had some meat left over, or we had some cheese left over, or we had multiple things left over in each situation. Those would be in excess. I want to take you through some situations on stoichiometry now. And here's our first example, silicon dioxide. Uh, when mixed with hydrogen fluoride, which that's a mistake, that should be hydrofluoric acid, makes water and silicon tetrafluoride. So I begin with that much hydrofluoric acid and that much silicon dioxide. The question is, what is the limiting reactant and what is the excess reactant? And I'm going to go out of the presentation now to show you the graph. So you have your normal stoichiometry table, just like we've already done. And we have, let me make this big as I can. And we have our normal, equation on the top. It's balanced. And we have our normal labels on the stoichiometry table. So from the previous slide, it mentioned that we started with 4.56 grams of silicon dioxide. So I want to change that. So I write that in that box, and we want to write that as far to the left as possible because of this new technique I'm going to show you. The problem also said we have 2.51 grams of hydrofluoric acid. So the technique is we want to carry on our stoichiometry calculations all the way over to the X, or all the way down to the X box, the carryover box. And so if I go silicon dioxide first, I find the molar mass of silicon dioxide. That would be a silicon plus 2 oxygens is 60.09. To find the moles, I take 4.56 divided by 60.09 in sig figs matter, and I get 0.0759 moles of that. The triangle row is the coefficient in front of silicon dioxide, and that's 1. So I go 0.0759 divided by 1, and my final number for silicon dioxide is 0.0759. And we'll see how that plays a role in our answer. Now let's go to the hydrofluoric acid column. And the molar mass is 20.01. That's hydrogen plus a fluorine. And I take 2.51 divided by 20.01, and I get 0.0125. And then the coefficient is 4 in front of hydrofluoric acid, so I go 0.125 divided by 4, and I get this carryover number, 0.0313. So here's where I think it gets easy. As long as you get the right numbers, as far as limiting reactants go, the smaller of our carryover numbers is our limiting reactant. So you can see I already have the answers to the questions down there. What is the limiting reactant? Well, it's the smaller number. And in this case, you would answer the limiting reactant is or equals HF, hydrofluoric acid. And we can shorten limiting reactant. Here on future slides, I will just say LR equals HF. Excess reactant is the higher carryover number, the higher X number, and that is 0.0759. And that answer to what is the excess reactant would be SiO2, silicon dioxide. So I hope that's pretty simple, where your limiting reactant is the smaller number, carryover number, and your excess reactant is the higher carryover number. Let's do a little bit more intense example. And here we go. Combustion reaction was performed with that much C6H6 and that much oxygen gas. What is the limiting reactant? And here's a new question. How many grams of the excess reactant is left over? So we have to do the same technique we just did. We have to figure out what the limiting reactant is and what the excess reactant is. And the problem said 36.8 grams of C6H6 and 41.0 grams of oxygen. So I write those in first. Then I want to take those all the way down to the X line. So same technique, molar mass of C6H6 is that. 36.8 divided by that number will give me 0.471. There's a 2 in front of that. So I take 0.471 divided by 2, and I get 0.236. So I have that number. Now I want to go to my oxygen, and the molar mass of oxygen is 16 plus 16 from the periodic table, 32. So 41 divided by 32 is 1.28, and then 1.28 divided by 15, the coefficient in front of oxygen, gives me 0.0854. Now, from this, we can now say that the limiting reactant, we can answer the question, is the lower number, and the lower number is oxygen. So you can see down here, my answer, LR, equals O2. Now, the second question to that was, how much of the excess reactant is left over? So here's the new technique. I said earlier, you want to write your numbers as far to the left of your box as possible, because now on our excess reactant, we're going to split it in half with a dotted line. So here's that dotted line. I split it in half. And that smaller carryover number, I am going to write in the box underneath C6H6. And I want to now take my calculations all the way to the number of grams at the top that was actually used in the reaction. So I still have a 2 here. I go remember, going up you multiply. So 0.0854 times 2 is 0.171. Then I don't have to do any new calculations. I take it 0.171 times the molar mass of C6H6 is 78.12, and I get 13.3 grams. That number means I used 13.3 grams of C6H6 in the lab. And the question is, how much of that C6H6 is left over? So if you look down here at the bottom, I have to go with my original amount, 36.8, and subtract how much was actually used, 13.3. So my final answer is there is 23.5 grams of C6H6 that is left over in this chemical reaction. That's how you do an excess reactant problem. Next, our final example before I make you do some work. So I have another reaction, and I begin with, you can see iron plus oxygen makes iron 3 oxide. So I begin with that much iron and that much oxygen. Now check this out. What is the limiting reactant? How many grams of excess reactant will be left over? And a new question, how many grams of product will be formed? How much iron 3 oxide will be made in this problem? So the technique is the same, where I write down the original reactant numbers. So the problem said there were 51.03 grams of iron, and there were 37.5 grams of oxygen. And again, you want to write those as far to the left of the box as possible. Same technique, I have to figure out what my limiting reactant is. So the molar mass of iron is 55.85. So same thing, divide those two numbers, and I get 0.914. Then divide by the coefficient of 4 to get my carryover number of 0.228. I do the same thing with my oxygen column. Molar mass of oxygen is 16 plus 16, 32. So 37.5 divided by 32 is 1.17. 1.17 divided by the coefficient of 3 gives me a carryover number of 0.391. So the smaller number is 0.228. That means our limiting reactant is iron, Fe. And you can see that answer down at the bottom. So we've answered the first question. Excuse me. Second question, how much excess reactant is left over? So we take that smaller number. We're going to put a dotted line right down the middle of the excess reactant column. So you can see that dotted line. I'm moving around. And I take that smaller carryover number and I put it in that box. And now I'm going to take it all the way up to the top, to the grams of oxygen. So the coefficient's still the same, 3. 0.228 times 3 is 0.684. The molar mass of oxygen is still the same number, so 0.684 times 32 is 21.9. That means we used 21.9 grams of oxygen in this reaction, but we started with 37.5 grams of oxygen. So how much is left over? You have to do the subtraction. 37.5 minus 21.9, and our second answer is 15.6 grams of oxygen is left over. The last question was how many grams of product was made? So that's the last technique we take. We still take that smaller number, the limiting reactant number, and we put it in the column underneath our product, 0.228. Now we want to take that all the way to the top, to the grams of iron 3 oxide. There's a 2 in front, so 0.228 times 2 is 0.456. The molar mass of iron 3 oxide is 159.7, so we go 0.456 times 159.7, and we get an answer of 72.8 grams, and that will be our final answer. Down at the bottom, this reaction produced 72.8 grams of iron 3 oxide. You should use this model when you do your limiting reactant problems. As you can see, I always put my answers outside the stoichiometry table. Good luck with your problems, and I think you will be successful. If you have any questions, let me know.